Hello everyone, welcome to another video. Today we're going to be introducing vectors. So a vector is a mathematical object that we will use, and it contains information like magnitude and direction. The simplest way we can represent a magnitude and a direction at the same time is with an arrow. So the arrow has a head and the arrow has a tail. The arrow has a length, and it also has a direction if we specify a reference frame, such as X and Y axis, because we can define an angle theta from which this vector points with respect to this X or Y axis. Now, we can add vectors. So this is typically called it's called vector addition. And we can add two vectors by connecting them head to tail. So if I have one vector, let's call it A, and then I have another vector, let's call it B, that is going to, when added together, give me the resultant vector R. And also the commutative property of addition applies to vectors. We can see if we switch the order that we add them. So if we do the B vector first, and then the A vector second, we end up at the same spot, and the R is still our resultant vector. Okay? Now, each vector in a plane, a two-dimensional vector, for example, is made up of two different components. The amount of dimensions that the vector is in determines the number of components that the vector will have. So a two-dimensional vector will have two components, and a three-dimensional vector will have three components. Let's start with the two-dimensional vector first. So these scalar components, let's say we have some vector A. The scalar components of this vector along the x-axis are going to be a sub x, and the y components are a sub y. That's what we use the subscript to denote. This is the magnitude of A. And we still have an angle to define. This is a right triangle, always. And our scalar components are as follows. We can calculate the magnitude by evaluating the square root of the sum of the squares of the individual components. And the slope of the radial vector is given by this inverse tangent relationship. Another thing worth mentioning, and we've kind of already seen it in our examples above, but if I have some plane and I have two vectors, well, really one vector, and I just translate it to a different spot on the plane, these vectors are equivalent. Because remember, a vector only contains information about the direction and the magnitude. It says nothing about where it is located on the plane. So the definition of a vector, or the result of a vector translation, is a vector of equal magnitude in an unchanged direction. They are therefore equal vectors. Now, looking briefly at three-dimensional case, typically I will start with an x-axis, and you will kind of imagine this going into and out of the page. And then I'll do a z-axis vertically and a horizontal axis, and I draw them such that they all intersect at the same location. And so if I have a vector that goes from the origin to this outer corner here, and I have this vector running perfectly through the diagonal of this box, and let's say my coordinate system is set up such that along the x-axis this is located at a coordinate A. Along the y-axis, there's a coordinate B, and along the z-axis, there's a coordinate C. That means that this point right here is A, B, C. And so if we call this point capital A, and let's call this O for origin, which is just at 0, 0, 0, we can actually say RA minus RO equals RAO. That's a vector, position vector, and it just equals A. Now I'm going to introduce the unit vectors. These are just vectors of length 1, but they specify a direction. So the I is associated with the x-axis, the j hat is associated with the y-axis direction, and the k hat is associated with the z-axis direction. All right. And then, so for example, if I wanted to take the magnitude of RAO, the magnitude of vector RAO, I could just take the square root of the sum of the squares. And oftentimes, more generally, you'll see this written as like, maybe, and then they'll use a subscript notation to denote the vectors that are associated, the quantities that are associated with the directions. And so again, you have the square root of the sum of the squares of the individual components. So vectors, this is worth mentioning, they can represent displacement, velocity, acceleration, forces, etc. That's why we use them in physics and engineering. And so I think actually this has been a pretty decent introduction to vectors. And then in the next problem, or in the next video, we will do a sample problem that kind of calculates all of this and it tests our knowledge. So leave in the comments anything that you would like me to clarify, and also if there's anything that you would like me to cover in the future, I would be happy to oblige. Thank you for watching. Have a great day. See you in the next video.